first ITC Colloquium of this semester, and we're very happy to welcome here Eric Peng, who came from Peking University, where he has a joint appointment at the Department of Astronomy and the Couple Institute for Astronomy and Astrophysics. So Eric is a world expert on globular cluster systems, and of course we know that historically globular clusters have been used to provide us some clues for how galaxies form, and were actually like the first evidence that now led to this standard paradigm of hierarchical growth of galaxies. But it was all done on like a single galaxy, the Milky Way, and it wasn't until Eric came around and studied 100 galaxies in the Virgo cluster and systematically provided us clues for galaxy formation from this large set of globular cluster systems. And most of his work has been on this topic since, but during his career covered a lot of ground, including as a graduate student at JHU. He actually discovered a stellar stream of young stars in Sen A. And as an undergrad at Princeton, he had a single author paper on inferring the sizes of solar sizes in microlensing events. These days, most of the diversity of his work is coming from the hosts of galaxies, where he studies globular clusters and other compact systems. So during the lunch, we'll hear more about the ultra-diffuse galaxies. And in this colloquium, we'll hear what the globular clusters have told us about the formation of the most massive galaxies in the local universe. So take it away, Eric.
All right, thanks for that nice introduction, and it's a real pleasure to be here. When I first chose the date and decided to come for the first week of your second semester, the comment I got from someone was, "You're choosing to go to Boston in winter?" But then I saw someone at Harvard Square wearing a T-shirt yesterday, so I think winter's over. Yeah, it's all right today. Yeah, it's really nice to be here and to have the opportunity to share some of the research that I've been involved in, particularly on the Virgo cluster, which is what I'm showing you here in the title slide, which I'm calling the belly of the beast, since the Virgo cluster is the largest mass concentration in the local universe within 35 megaparsecs. And this galaxy here is M87, which is the CD, or the central galaxy, the galaxy sitting at the center of the hot X-ray gas. And I'm sure you've heard a lot about this galaxy in different wavelengths here at the CFA. But I'll be focusing mostly on the things that are falling into it and things that are building, that are assembling these kinds of massive galaxies. And of course, this work is done in collaboration with, well, I guess today's it's not such a large team, but with the Next Generation Virgo Cluster Survey team and some of the members of my group here, former members of my group. So the picture that we are trying to put together here, particularly for the very oldest stellar systems, is to try to understand the kind of star formation that happened likely at very high redshift. Now, this is a fairly old picture from Ben Moore's 2006 paper, but it was just a dark matter simulation, so all this stuff still basically holds. The idea is that when you're looking at old systems like globular clusters or dwarf galaxies, some of them, or a lot of them, we think may have formed in the earliest collapsing peaks at high redshift. Now, this is, say, redshift 12, where this group of authors identified halos, mainly like small, low-mass halos that have already collapsed because they're in a very overdense region of the universe, and may have hosted some of the first star formation. Perhaps not the first stars, but certainly things like population 2 stars, or the old stars that we see in the Milky Way halo. But when you track these low-mass halos to the present day, you'll find that most of them are already at the centers of large galaxies. And so that's where all these green dots are associated with some of these low-mass halos that collapsed at high redshift. A few of them survive as satellite galaxies today, and we would identify them today as dwarf galaxies. So taking this picture from our cosmological picture of galaxy assembly and trying to map that into galaxies today, we have to try to find the right analogs. But the thing is, we don't really know how globular clusters and dwarf galaxies form, so we're trying to come at it from both angles. So a high mass galaxy like M87 really is kind of assembling, swallowing everything that's hitting into the middle of the cluster. And so it's a great place to study the effects of environment and also to study how the outskirts, particularly of massive halos, massive galaxies form. And that's what I'll be focusing most of the talk on, to try to understand how you're forming not so much the metal-rich, dense nugget that's at the center, but the rest of the galaxy that's been assembling over Hubble time. And this is, of course, a galactic globular cluster, and you have to, just to remind you, globular clusters are pretty interesting for almost every topic in astrophysics. Historically, they've been very important for stellar evolution, the age of the universe. Now they're probably sources of, they're binary factories. They make things that will probably be detected in gravitational waves one day. So they're one of my favorite topics in astrophysics. And one of the nice things about them is that they're very dense. So observationally, they're very easy to see, even at large distances. You may be able to see that this galaxy is peppered with little faint dots. Those are the globular clusters themselves in M87. And I'll also be talking about dwarf galaxies, low-mass galaxies, some of which have their own globular clusters in them, as well as sometimes a nuclear star cluster. So that's quite an interesting phenomenon itself. Now, when we talk about the hierarchy of galaxy assembly, one way to understand it as the food chain of galaxy assembly, right? Because these objects, get eaten in a sense. And when you talk about real beasts, we talk about M87 figuratively as a beast in the local universe, as a fossil of galaxy formation. Well, this is a real beast and a real fossil that I found online. This is this creature was a fanged fish of some sort that lived in the late Cretaceous period and was extremely large, about 20 feet long. And what makes this particular one interesting is that one version of it was found with a recently eaten fish in it, also fossilized. So this is just to show that if you want to understand the beast, it's also good to know what it has consumed. And so all of this is fossilized, and I think that's a good analogy to what we're doing with the local universe when we look at massive early type galaxies and their stellar halos. As a word of caution, paleontologists think that the reason why this is so well preserved is because this beast bit off more than it could chew, and the struggling of this smaller fish ended up killing it. So, cluster central galaxies, we still see the mass assembly going on, right? We can see things merging in. Some of the most violent and energetic processes in the universe are in galaxies such as this. And in some ways, they're seen as the end state of galaxy evolution. Now, on the other end of the mass spectrum, though, we have these low mass objects that we think formed early, that they're sort of surviving from these progenitors, right? That they're hard to destroy, or at least they haven't been destroyed yet. And particularly these compact stellar systems are of interest. Globular clusters and their cousins, we think they're related, ultra-compact dwarf galaxies. These are some of the densest stellar systems in the universe, and so they're robust survivors, right? You can throw these things into a galaxy, and if they're not on entirely the wrong orbit, they can survive longer than a Hubble time. So I think also we have to keep in mind that every time you see one of these stellar systems, it didn't form in isolation. So globular clusters and their ultra-compact dwarfs, also these sort of more massive cousins of theirs, are kind of lighthouses that signal the presence of unseen structure. And I think this is a fairly older version of the PANDAS survey, which is a survey of the nearby M31 halo, where they mapped to very low surface brightness levels the stellar halo of M31 using RGB stars. So you can get much fainter than you can in integrated light. And this map shows, this is M31's disk in here, and these are the streams, some of the streams that they found. And these red and blue dots are, in fact, new globular clusters that were discovered in this survey. And I think one of the striking things is that everywhere you see one of these dots, you can kind of cross your eyes and also see some fluff of stars here. And that's not unexpected, because we think that globular clusters must form in the galactic environment. And so if they've been accreted into the stellar halos of galaxies, they should follow also a trail of stars, except that this trail of stars is typically very difficult to find. but they're an easy way to see the kind of structure that you expect through the hierarchical assembly of galaxies. So I kind of want to, in this talk, address a few questions here. So we are interested in the origins of these compact stellar systems. Where do they come from, and what can we learn about that? And then also the interplay of being in this massive galaxy. What is it like to be one of these low mass galaxies? So the interplay between these two ends of the mass spectrum, and then how do these massive galaxies assemble from their smaller components? So the data that I'll be presenting to you is part of a CFHT large program. So the Canada, France, Hawaii telescope, which is pictured here on Mauna Kea, conducted a large program. It's something, well, at this point it's about 200 nights on the telescope over 6 years, where we did a deep survey of the nearest cluster, the Virgo cluster. And actually this is our data superimposed on the sky where the Virgo cluster is. M87 is that dot right there in the center. This is a very deep survey, and in fact, until we performed this survey, the reference for this nearby cluster, the nearest cluster, was the Virgo cluster survey done by Bingley in 1985 using the 2.5 meter DuPont telescope on photographic plates. So this is a great step forward, and it's also multi-band. And one of the great advantages we had, because CFHT is done in Q, is observed in Q, is that we could specify the image quality in the I-band to be less than 0.6 in all the fields. So we have exquisite spatial resolution from the ground, where the full width half max of our typical full width half max is about 43 parsecs, which means that we can resolve structures as small as 10 parsecs. And that's crucial for some of the work I'll be showing you here on the ultra-compact dwarf galaxies. So we also have some K-band imaging in the central regions, which is also quite useful. Now, I'll be focusing in this talk on just this central region, so what we call the Virgo cluster core. And this is a zoom in, a color zoom in, which is similar to the region I showed you in the title slide with M87 in the center. And this is a chain of galaxies nearby. That's there's one famous one being tidally harassed here. And this region is 2 degrees on either side, which is about half a megaparsec or so. You go very deep, like Chris Mijos has done with the Borel-Schmidt telescope, you find that this region, while seemingly just empty space between galaxies, is filled with stars, filled with streams, intra-cluster light. So it's a very active portion of the galaxy cluster. And to give you a sense of scale, this is an HST image of M87. So the central region, you can see there is the AGN. There's a jet coming out here. It's quite famous. So this is just an ACS image with HST, 16 kiloparsecs. And that's the region that I'll be talking mostly about today, which is much, much larger. Now, as I showed you before, there was a ton of interstellar, sort of intracluster light there. But now, with the NGVS data, we can, going very deep, we can pick out compact sources and identify those that are likely to be globular clusters or UCDs. And that's what this field looks like when you plot every globular cluster candidate down to, in this case, 24th magnitude. So this is roughly half of the globular clusters in this region, and numbering roughly, I think it's about 8,000 objects in this plot here. And I don't know if you can see it, but of course there's the population associated with the central galaxy here. But as you get out into the halo, you start seeing, it starts seeming a little bit less smooth, and you can almost, you can identify by eye some of the dwarf galaxies that are in the field that have their own globular cluster populations. You can certainly see the massive galaxies in this chain up here that have their own globular clusters. So this is a leap forward in terms of the kind of data that we can use to study globular cluster systems and compact stellar systems in general in these nearby galaxies. To give you as reference, the survey that Anna talked about in her introduction about how we had looked at 100 galaxies in the Virgo cluster, we'd done that with HST, and that was just in that small little field that I showed you at the beginning. So now we're expanding this to a wide region to get a look at the environments of these galaxies and also all their neighbors. So first I'd like to address the topic of ultra-compact dwarf galaxies, since this is something that was quite of interest over the past 15 and 20 years. So ultra-compact dwarfs, or UCDs, on their surface they look just like globular clusters, except they're quite massive and they're fairly large. But if you look at these dwarf galaxies, these kinds of dwarf galaxies, you find a nuclear star cluster in the center, which also on its surface looks kind of like a massive globular cluster. But we now know that their stellar populations are a bit different, being at the centers of galaxies. They may not be quite as old. They may have multiple star-forming events. And when you look at UCDs that are kind of massive star clusters without this envelope of a galaxy around it, the question arises, are they just the massive end of the globular cluster mass function, or are they remnants of galaxies? So this has some implications for what you infer kind of the initial mass function of galaxies is in the cluster, right? So if every one of these things represents a single galaxy, well, it's interesting then how it maps onto, say, simulations and dark matter halos. Like you'd expect then that perhaps these things once hosted their own dark matter halos, or much larger at some point. On the other hand, if they were just one of the most massive star cluster in a larger system that formed, you may not think of them quite the same way cosmologically. And this is now a fairly old diagram, but it nicely represents the sort of family of objects that we're interested in here. This is luminosity or stellar mass, so getting more massive on this end, more luminous here. This is size here. Now globular clusters appear to have basically no size-mass relationship. They have a mean size of about 3 parsecs. These are galactic globulars and these black dots, and then also Virgo globular clusters here. But when you get to the more massive end, you start seeing this relationship start here. So now, as you get more massive, things get larger. And these objects here are what are typically called UCDs, these ultra-compact dwarfs. As you go along this even further, you get into very massive UCDs, or what people would start calling compact ellipticals. So M32 is on this sequence as well. And then you get here the main size-mass sort of locus of early type galaxies is this here, all the way down to local group dwarf spheroidals down here. So these objects are much more compact. They're kind of intermediate between galaxies and star clusters. And so, naturally, we want to know what they are and what does the existence of these objects tell us about either galaxy or star cluster evolution. So one way to go at this is to look at the core of Virgo, because this is a place where we have the most UCDs of anywhere in the nearby universe, out until you get to the Coma cluster. And so in this region, we have thousands of globular clusters, as I showed before. So we don't have kinematics or confirmation for all of them. We do, though, through the efforts of many, many people over decades, have roughly 1,000 globular clusters with velocities in this region. So one thing that we made a focus of is to try to get a velocity for every UCD in this region to try to compare these two populations. If UCDs really are just massive globular clusters, you might expect that they would basically trace the same kinematics and basically be the same as globular clusters, except being more luminous. So we were able to select UCDs based on their size, because we have this very good image quality. And we got velocities we have velocities for nearly 100 of them now, which is over 3 times more than any previous sample. So it really allowed us to do some statistics. And this work was led by my former postdoc, Hongxin Zhang, who's now in Chile. And so what did we find? Well, somewhat to our surprise, we found that the UCDs have very distinct kinematics that are different from those of globular clusters. This is just a velocity map of the UCDs versus the globular cluster systems, showing whether there's any bulk rotation. Now these are hot stellar systems. You don't expect to find very much rotation in them. But when you compare these populations, and here the globular clusters have been separated into blue and red. Typically UCDs have colors similar to blue globular clusters, so metal poor globular clusters. So that's the comparison we often use. And the metal poor globular clusters here have very little net rotation in these regions here. You can see this is the angular momentum vector. You just see it's not very much rotation here. The UCDs, however, show a much stronger rotation. I mean, they're still pressure-dominated systems. I think the rotation amplitude here is something between 30 and 50 kilometers per second, whereas the dispersion is of order 200, 300. So, but you can see a definite rotation signature in here with an angular momentum vector that's different from either the blue or the red globular clusters. And so what this tells us is that these massive star cluster-like systems, these UCDs, have entirely different kinematics from the sort of normal star cluster population. And so that implies that maybe they're not just an extension of this star cluster population. Now you can look at, just by eye, the line of sight velocity distributions of the UCDs versus the globular clusters. The globular clusters have sort of more Gaussian-like velocity distributions, as shown by these blue dashed curve here, whereas the UCDs have, one way to look at it is that they have more kurtosis in their line of sight velocity distribution. So you can do a genes modeling analysis of this, and when we do that, we can look at the anisotropy. So the shape of the line of sight velocity distribution sort of roughly translates into the shapes, the eccentricities of the orbits. So this beta parameter here measures how radial or tangential the orbital distribution is as a function of the radius of the galaxy. And roughly speaking, low values here, negative values mean circular orbits, and high values mean radial orbits, or very eccentric orbits. And whereas 0 means you have a sort of equal mix of both. And I would like you to concentrate on the black line here. That black line is the UCD population. So the UCDs have very tangential orbits, so circular orbits at the center. But as you go further out, you end up with more radial orbits, so more plunging orbits. The blue globular clusters also have tangential orbits in the center, but when they become sort of isotropic, but at large radii, they're still tangential. So not only is there difference in these sort of bulk rotation properties, but in the general average eccentricities of the orbits in the outer regions, you see quite a bit of difference here. So how would we interpret that? Well, you can just sort of imagine that your average metal core globular cluster here is on more of a, I mean, this is obviously an approximation here, but more of a circular orbit in the outer region. But then if you had some sort of UCD-like thing, it'd be on more of a plunging orbit. And that's very, now it's very suggestive, because one of the ideas is that UCDs are in fact the stripped remnants of dwarf galaxies. And in a different study, led by another former postdoc of mine, Cheng Liu, we looked at the photometry of UCDs in the M87 system. So we were identifying these UCDs based on the central component here, this slightly resolved bright component that we're calling an ultra-compact dwarf. But when you look more carefully at them, you see that they don't all look like isolated compact objects. In fact, a lot of them have what what you would call a stellar envelope. They have the central core, but then they have this faint fuzzy stuff around it. And in fact, if you start with a nucleated dwarf, so this is an actual nucleated dwarf galaxy here, like the one I showed you in the previous slide. But then you have nucleated dwarf galaxies. You can make a morphological sequence of sort of nuclei plus envelope, all the way down until you get to something which we call a naked ultra-compact dwarf. And if you look at the surface brightness profiles here, you can see there's the dwarf galaxies, and then a sequence that goes down until you basically get a compact source here. And we think this is very suggestive as a UCD morphological sequence. Because when you look at where these things are now, and their distribution, their distance from the center of M87, you find that, okay, so if you look at the full sample of dwarf galaxies are with nuclei are at larger radii. But then now you look at objects that are identified as UCDs but have visible envelopes. They come closer to the center. But the objects that make it all the way to the center are UCDs with no envelopes. So there seems to be a radial gradient in the in the amount of sort of stellar envelope you have associated with this central massive compact stellar system. And by massive, I mean it's 10 to the 6, 10 to the 7 solar masses. In fact, when simulations, so people run simulations, this is a simulation by Joel Pfeffer and Holger Baumgart, investigating exactly this scenario, taking a nucleated dwarf galaxy, throwing it into the center, the cluster potential, and seeing what happens. They find the surface brightness profiles over about 2 gigayears can evolve from something that looks like a nucleated dwarf galaxy down to something that looks like a massive star cluster. And so, I mean, all of these things were done totally independently. There's a remarkable similarity there. And this is just a nice picture illustrating these objects. Like out here, we're seeing sort of objects with very prominent envelopes, but then when you get closer to the center, that stellar envelope goes away. So, you know, once again, we're looking at this massive galaxy and how it's kind of accreting these dwarfs and possibly then leaving only these remnant nuclear star clusters. We think it shows that at least some of these objects show evidence that there's this accretion going on. So, having talked a bit about the massive end of the spectrum for UCDs, I want to move on to sort of regular globular clusters and to see where they come from and how they're accreted into the galaxy and what that tells us about galaxy assembly. So, I think most of us know that globular clusters are massive star clusters, and they form mostly, we think, in massive star-forming events. Right? So it kind of follows that globular clusters should trace star formation in general. And this is a local starburst, dwarf galaxy, NGC 1569. It was a very famous starburst, and it has a few of these, what some people at one point termed superstar clusters or protoglobular clusters. It's likely that these massive star clusters will one day survive to be something that looks like a globular cluster today. So star formation happens in star clusters, and if you have a massive event, you'll form a massive star cluster. So, you know, something we write in all of our proposals is that, oh, globular clusters trace star formation. That's great. We can learn about the star formation history of the galaxy. But actually, you know, it's sort of true and it's sort of not true. Right? So if globular clusters faithfully traced the star formation of a galaxy, then you might expect that the ratio, say, of globular clusters to field stars would be the same everywhere, right? It's just some fraction of the stellar mass goes into a massive star cluster. But that's not what we find, right? There's this number that's been termed the specific frequency of globular clusters, which is basically the number of globular clusters per unit stellar mass or stellar luminosity. And it's this horrible thing here, but basically you have to remember that if a dwarf galaxy, or if there's 10 to the, well, if there's minus 15, so an MV, an absolute magnitude of minus 15, which is something like 10 to the 8 solar masses, has one globular cluster, then this number is 1. And it's defined in this way so that the Milky Way roughly has a specific frequency of 1. And so usually everything's defined so that the thing that you know is unity. Right? So that's what specific frequency means. And when you look at this across galaxies of all kinds of stellar masses, and now this is kind of a messy plot, but from Georgiev et al., where he compiled lots of galaxies from the literature and then some of their own data, basically have high mass galaxies here, low mass galaxies here, and you know these are the mean relations. Basically, the takeaway here is that these points do not lie on a single line. Some galaxies have 10 times, or maybe even 100 times, more globular clusters per stellar mass than others, right? The Milky Way is down here, near 1, and you know, M31 is here, but then these are massive elliptical galaxies, like M87 is somewhere in this group, and then you have a lot of dwarf galaxies with very, very high numbers of globular clusters. Yes?
But there was a claim that the number of globular traces the black hole mass of galaxies. If black holes correlate with spheroids, wouldn't you expect that they represent a fraction of the spheroid mass?
Right, but so in these galaxies at least, I believe the entire galaxy is the spheroid.
Right.
So
there should be a correlation with spheroid mass if you believe the correlation with black hole mass.
Right. I think I'm not sure what to think about the correlation with black hole mass. I feel like
They claim it's very tiny.
yeah, they do, yeah. But it could be that they're both correlating to something else, like halo mass, perhaps.
Well, it doesn't matter, but in this plot, spheroid should correlate with the number of probabilities.
Well, well, so what you're seeing here, though, is that, and I think also the case for the black hole mass is that basically galaxies that, the most massive galaxies, like the brightest cluster galaxies, you're hitting the exponential cutoff of the mass function. So all those galaxies have the same stellar mass, but they can have widely different globular cluster populations as well as different black hole masses. And it's possible then that those are correlated. I think here, you're not going to get galaxies that are much more luminous than here, but these galaxies can have different black hole masses and different globular cluster numbers. I think that's what's going on. So the takeaway though, is that globular clusters don't form as a constant fraction of the stellar mass, right? They have this sort of U-type relation here. Now that U may look familiar to those of you who've seen the stellar mass halo mass relation, right? And this alludes to the point that we were just discussing, which is that if you take the stellar mass halo mass relation and sort of infer halo masses for these galaxies and then compare them to the numbers of globular clusters, so people have done this, you find that the number of globular clusters, or maybe the mass of the globular cluster system as a whole, scales with the halo mass. And so this has been something that has been used a lot, actually, as in the past few years, just the past few years, people are now using the number of globular clusters to infer the halo mass of galaxies. And this is just from a more recent paper, a Harris paper, where they take a number of galaxies in the literature and calculate the mass, or the number of globular clusters, divided by the inferred halo mass. And I keep saying the inferred halo mass because these are not measured halo masses. We have to remember that. And then they divide the two, and it looks like, yeah, I mean, they're constant, with the scatter of about an order of magnitude or so. But certainly, they seem to trace what you'd expect the halo mass to be, certainly better than they trace the stellar mass. And so that makes them quite interesting. I just, for those of you who've heard about this, I wanted to put out a few caveats. Remember, for these galaxies, M halo is not really M halo. These are stellar masses that have been translated to halo masses using some calibration, either from weak lensing or maybe just the general stellar mass halo mass relation. And all it does is it takes this U, maps it onto another U, and then flattens it, right, until you get this. But the fact that that works is interesting. There are some measurements of mass, dynamical masses using stellar dynamics, but those don't give you real halo masses either. Most of those are in regions where it's still baryon dominated. And also most of the galaxies where these have been studied are satellites, whereas the stellar mass halo mass relation typically uses from centrals. Maybe that's not too different, but that's something also to keep in mind. And also it doesn't take into account any potential scatter in the stellar mass halo mass relation. So those are some of the caveats. Yet at the same time, it is interesting that you can get this. Now traditionally, this specific frequency problem, which is how is it that you can get more globular clusters per unit light in this kind of a galaxy than you can in other galaxies like the Milky Way, people have proposed that, well, if you form globular clusters efficiently in late-time mergers, right? So in the antennae here, you form lots of star clusters, these metal-rich star clusters, and these massive mergers, then you can boost the number of globular clusters per unit light. But now we pretty much know that this is not the solution. If you can produce globular clusters this way, you can produce the metal-rich population here, and there's an increased efficiency there. But when you look at this is a very similar plot from a specific frequency with luminosity again. This is just for the Virgo cluster sample. You look at M87, and it's this high. The only other objects that we see that have specific frequencies this high are these low-mass galaxies here. And in fact, when you look at these massive galaxies, their abundance in globular clusters is always in the metal poor ones. It's not the ones that form in this kind of an event. They're the metal poor ones that must have formed in low-mass halos very early on. So we think that there's some connection between these galaxies and the overabundance of globular clusters here. And this is just a lot of information here, but you've probably heard that globular cluster systems are in massive galaxies at least, are generally bimodal in their metallicity. You have, this is a map of the sort of histogram of globular cluster colors. You can think of this as metallicity. So this is low metallicity, high metallicity across a number of galaxies here. So one of these stripes here is the histogram of metallicity or color for a globular cluster system. And you see there's like a blue mode and a red mode here. So this is this bimodality. And this bimodality sort of tracks galaxy mass. Now the interesting thing about these globular cluster systems is that we know that massive galaxies are metal rich for the most part when we measure them, right? But most 2/3 of their globular clusters are metal poor. And so all galaxies appear to have this kind of metal poor population, but the metal rich population scales with the stellar mass, and also you can see the actual metallicity scales with the stellar mass. So the fraction in the metallicity, this seems to be consistent with what we call an in situ formation, where these metal-rich globular clusters are forming with the bulk of the spheroid that we know and love, this metal-rich spheroid. But these metal-poor objects, they're ubiquitous, and they actually dominate these globular cluster systems. So there's definitely some sort of efficiency difference going on here, where you're forming, clearly a majority of the stars in the galaxy, these massive galaxies, are not metal-poor, yet the majority of their globular clusters are metal-poor. So there's some sort of mismatch there. And I think this is what makes these globular clusters interesting as probes of galaxy formation, right? They're telling us something different. So we decided to look into this a little bit. Again, M87 particularly has is the highest specific frequency in the local universe. And we think that the solution, or at least we can get some answers by looking at objects in this range. Now, you may say, oh, well, yeah, there's kind of this U-like relation here, but actually there's a lot of scatter here. Some of these objects have no globular clusters, these low-mass galaxies. And some of them have very high numbers of globular clusters. And so if you take just that low-mass range and plot it versus the projected distance from the central galaxy, you start seeing some trends. And the one that we noticed the most was that of the ones that have high numbers of globular clusters, they're all mostly toward the center of the cluster. They're actually pretty close to the center of the cluster. And that was pretty suggestive. Because, it's much later work, but I'm sure you're familiar with this. This is work done by Priya Mastani with Lara Salas, using a lustrous looking at dwarf galaxies in clusters and their star formation histories. And what they found was that if you look at, say, the correlation of the burstiness of the star formation history against the density of the environment, that these dwarf galaxies, or these low-mass galaxies that lived in a cluster environment, in these dense environments, had a much wider range of burstiness. So you can have some very bursty star formation histories as compared to those in the field, right? Those in the field seem to have more quiescent star formation histories, but at high densities, you can get this very intense star formation here. And what happens then is, in this picture that they developed, these cluster galaxies, they have this very strong peak of star formation early. This is star formation right here. But then they get quenched, right? They fall into the cluster and they get quenched, whereas the field galaxy will continue forming stars until today, right? And then there's everything in between. Those in sort of intermediate environments probably have less of a burst and then get quenched later. So if you think that you can only form globular clusters you need a starburst to form globular clusters. You can't just, the Milky Way disk today is not really forming massive clusters, except maybe in the very center. So you need some sort of intense event. These objects are the ones that are most likely to form these globular clusters, and you can see that there's this correlation with environment. So there's a test we can do here, right? If you need bursty star formation histories or more truncated star formation histories to form these globular clusters, we can make an observational test here using the alpha to iron ratio. So when you look at galaxy halos, right, this is work by Jenny Green, looking at the M87 halo, in fact, At high metallicities, the alpha to iron ratio is a bit lower. This is a confusing plot, but basically this is the track you want to follow here. And at low metallicities in the halo, you get this sort of high alpha to iron ratio, implying that, and we see this in our own halo, where the alpha to iron ratio of stellar halos tends to be, twice solar or so. But one of the problems, or at least one of the mismatches that we have observationally, is that dwarf galaxies tend to have alpha to iron ratios around solar. So in this plot, we're talking about down here versus up here. And the alpha to iron ratio, just as a reminder, measures sort of the time scale of star formation, where you have high alpha to iron ratio due to supernova type 2 ejecta at early times, but then once the type 1As start, then the alpha to iron ratio goes down. But if you truncate star formation here, you'll end up with a mean alpha to iron ratio that's quite high. But if star formation sort of continues on and truncates around here, the mean ratio will go down. So that's how it's a clock in a sense. And this is just showing in the local universe where the surface density of star formation is high, we expect a larger percentage of our stars to be in massive star clusters. So again, globular clusters preferentially should be in bursts, and so we might expect them to have these high alpha to iron ratios. This is work led by my former PhD student, Yiqing Liu, who's now a postdoc. And what we did was we selected a few of these galaxies here to get very high signal-to-noise spectra to investigate these abundance ratios. And this is just spectra, just to show you that they look good. And this is what we found. I know this is not, this plot looks very similar to the other one I showed you, but actually what it is, it's not globular cluster specific frequency. This is now the alpha to iron ratio against the distance from the central galaxy M87. And you can see that in the outer regions here, so beyond about half a megaparsec or so, the alpha to iron ratio is similar to what we see in the local group. It's solar or even subsolar. But then within about half a megaparsec, you see the steep rise. This red point here measures that's the alpha to iron ratio of M87 itself. So what we're seeing is that the galaxies that are closest, these low mass galaxies closest to M87, have either, however you want to call it, burstier star formation histories, or maybe more rapidly truncated, more rapidly quenched star formation histories. They have shorter star formation timescales. Modulo, of course, there are other ways to get different alpha to iron ratios, like IMF variations, but then there would have to be some sort of environmental IMF variation. We can compare the alpha to iron ratio to the specific frequency, again, of globular clusters, and it's sort of what we would expect. The objects with low numbers of globular clusters have a low alpha to iron ratio, but then the burstier, shorter time scale star formation objects have higher numbers of globular clusters. So I think what this is telling us is that this ratio of globular clusters to starlight, the specific frequency, it's not about the globular clusters, actually. It's about what happens to the field stars. So globular clusters, they trace what you might call peak star formation, which generally happens early. They trace the most massive star-forming events. So specific frequency then tells us about what happens next, because a lot of the stellar mass in a galaxy will be forming in these non-bursty events, in these, sort of the tail of star formation that happens over most of a Hubble time. But if you quench early, then you just lose that stellar mass, and you end up with a high amount of a high specific frequency, because all those globular clusters, they've already formed. They weren't going to form in that tail of star formation anyway. So that's why this, the efficiency of star formation, so the stellar mass-scalar mass relation, seems to relate to the specific frequency relationship. And so we have this picture where the specific frequency traces the field star formation and the early quenching of the star formation. And then the metal poor halos of massive galaxies, then, they're made up of these low mass things that bursted, formed globular clusters, then maybe got quenched very early because they've fallen into the cluster, or they've fallen into this massive galaxy. They didn't have their subsequent star formation, and they get accreted. So in in low density environments, maybe you get a dwarf galaxy like this, which, these two have the same stellar mass roughly, But this one, and you may be able to see, doesn't have very many points around it, no globular clusters. This one has a lot of globular clusters in it. So as you get closer to this massive galaxy, you get systems that are more like that. Now this is, I know I'm in a theory center, so I just brought a cartoon. I didn't bring any theory. So this is just the basic idea, is that you have young galaxies in the early universe that say have different, they're different halo masses, so they have different initial total gas masses, right? So this one has sort of more gas, this one's a lower mass system. And the number of clusters that get formed roughly are in proportion to the total baryon fraction, right? So you have more gas here, you have more clusters here. Less gas, fewer clusters. But then, let's say here you're in a massive cluster, you fall into this cluster, you fall into the halo of the central galaxy, and you have rapid quenching. So you didn't really form very many field stars. You only end up with this amount of quenched, these sort of red stars here. That's what you're left with in stellar mass. But you still have all the globular clusters that you formed. Whereas this galaxy, in a low-density environment, continues to form stars and ends up with the same stellar mass as this other one. But it only had 2 globular clusters or fewer globular clusters because the initial gas that it had to start with was less. So these galaxies today are both old. They have the same final stellar masses, but they'll have different alpha to iron abundances, and they'll have different specific frequencies. And then they fall in, and they make up the halo of these massive galaxies. And of course, the massive galaxies, they themselves are the dense environment. So kind of by definition, the objects that are falling in and making up the halo of M87, so the metal poor globular cluster system, will be high specific frequency objects. So you can really elevate the number of metal poor globular clusters in the halos of galaxies compared to, say, some of the survivors that you're looking at today that maybe don't have very many globular clusters, except for the ones that are just about to fall, the ones that are still left, but maybe have a few gig years left. And so it's this combination of the metal-rich population, right? So these globular clusters formed in situ. There's what we call the metal-rich population, and then you have this accreted system that is created, 2/3 of the stellar halo, essentially. And that's what we're looking at here when we're saying these metal poor systems here being added on with these metal rich ones. So these objects here are creating the high specific frequency systems here. And so it really points to this, the fact that nearly every galaxy above a certain mass has what we would call metal poor globular clusters, shows that there's probably this kind of universal epoch of bursty star formation in low mass galaxies that happened, and that this has subsequently been accreted. Around massive galaxies, they've been accreted in, and they've had their field star formation truncated. Now, what are these globular clusters like? So I'd like to briefly highlight some work done by Matthew Pawelka, who is a recent PhD at Strasbourg working with us. And this is just another picture of a way of showing the thousands of globular clusters in the M87 system and the Virgo core. And this is work that is the best kind of work, which just happens serendipitously, right? You're trying to do something that seems obvious and it doesn't seem to work, and then you discover something. So what Mathieu's original thesis work was supposed to be was to take these globular clusters, their colors, and use them as a fiducial to test stellar population synthesis models. Because most population synthesis models are calibrated to the Milky Way globular clusters, right? If you can't reproduce the Milky Way globular clusters, then no one will use your model. But there are only 160 or so Milky Way globular clusters. It's hard to get integrated colors for them because they're resolved, there's the Milky Way in the way. So we thought here we have thousands of globular clusters in M87, all with very precise colors. We could define a new sort of fiducial to test stellar population models. And so this is what that is. These gray points are carefully selected high precision photometry globular clusters from M87. And this red line is the fiducial that we have, and all these panels are different models, right? So your favorite star formation, stellar population synthesis models. And most of them don't do all that well, actually. And this is just getting G, R, and I broadband photometry. But then when we looked at the globular clusters and broke them down by environment, so say the ones that are very close into M87, sort of intermediate distance, ones that are further out, and then ones associated with other different galaxies, we found that actually their colors change. So this throws sort of a wrench into the idea of comparing to stellar population models. But what you're seeing here is that a typical color like G minus R is what people use to separate, say, metal poor. Metal poor would be on this end, this is metal rich. But then now we're plotting against I minus Z. And you find that the central regions, like this black line here is the Milky Way globular cluster, a few Milky Way clusters. And this blue line is one set of models here. So you can use that kind of as a reference. In the very central regions of M87, you have they're very red in I minus Z. For the same G minus R, they're very red in I minus Z. And as you go to less dense environments, this goes down. Until in the outer regions, and in these other galaxies, you find the globular clusters basically match the Milky Way system. So there's something going on. These globular clusters, maybe it's abundance variations, maybe it's age, probably not age, but maybe it's the IMF. Something's different about the globular clusters at the center of M87 compared to, say, less dense environments like the Milky Way or the outer halo here. And that's still an open question. So I just want to wrap up with just a view to the future and some things that are going on that I think are fun and exciting that we're involved in. This picture of thousands of globular clusters, I really love it, as you can see, because I've showed it many times. And we're trying to do something very similar for the stars. And this is with a postdoc in my group, Alessia Longobardi. We now have time this semester to observe this entire region for planetary nebulae. Planetary nebulae are post-AGB stars that are actually quite easy to observe because they have a bright emission line, the O3 emission line. You can observe individual stars and then get very high precision velocities for them, even though they're quite far away. So we anticipate that when we get this data, we'll have a similar number, maybe 4,000 or 5,000 individual stars, planetary nebulae in this region. And one of the big advantages is that we'll be able to get velocity precisions 1 to 2 kilometers per second. So we'll really be able to trace, in phase space, a lot of the structure that you might see with your eye here. Whereas we can only get about 1,000 velocities per globular clusters, we should be able to get a velocity for every planetary nebula that we see. And then to touch on the idea of star formation histories and gas quenching in these dense environments, I'm involved with Thomas Puzia. We're co-PIs on a China-Chile joint research program where we are now in the process of installing an H-alpha filter on the dark energy camera to look at diffuse ionized gas in groups and clusters to see what's happening. How are these galaxies being quenched in these environments? And our goal is to use this huge imager that's down there to survey a lot of the local groups and clusters down to tens of megaparsecs. So that's just getting started. And then I'll finish with some of my conclusions here. And I hope I've gotten you interested in globular clusters and stellar halos and what they tell us about the assembly of galaxies. And I just want to highlight that we only have a few galaxies where we can do this right now, but we're hoping in the future to expand the sample much more greatly and get a better understanding. I'll stop there. Thanks.
Okay, Benedict.
That is very nice. I have a comment and a question about it. So the comment is you assign all the differences in sort of star formation quenching after a galaxy's fallen into a cluster. And that's of course one aspect of it. But actually it's been shown that you can explain a big part of it just by their selection. Like these galaxies that end up falling into a cluster are not random objects. And a lot of them would have had a very quick and short star formation history anyway. So it's sort of, in terms of structure formation, it's not all about quenching. Anyway, I understand why those early forming high globular cluster objects would go on small orbits. I mean, they're just like the cluster is smaller, but the star is a smaller dynamic at a time. But why is it that the UCDs, I mean, I guess they would have fallen in later, so they would be on a bigger orbit. But then why would that orbit be so much more radial as you showed?
So, I mean, I think it's possible that, because the criteria, if you're starting with, say, a normal dwarf galaxy, right, then it's possible then if you're at these large radii that you just need to have the pericenter be close enough so that you can get rid of the rest of the galaxy.
Selection effect.
Well, not an observational selection effect,
Right.
but like in nature selection, like nature has selected these things. Yeah, I think it's something like that. And I think in the inner regions, their orbits are circular or tangential, and I think that's a natural selection effect as well, because I think in the inner regions, if your orbit's radial, you're destroying the UCD, and I think you're not seeing it. And once we see that in the globular clusters too, because the density profile in the globular clusters at the very center flattens out.
Sorry if I just missed this, but do you have constraints on what fraction of the mass is stripped from the UCDs when they fall in? Like of the total solar mass they start with?
Yeah, so, well, for the UCDs themselves, we don't know what their progenitors were, but we can talk about a typical dwarf galaxy that has a nucleus. In that case, the nucleus is only a few tenths of a percent of the total stellar mass.
Nicole?
So, very nice talk. Thank you very much. I was curious about, is there also correlation between the nucleation fraction and the location or this specific frequency?
So you're talking about whether a galaxy is nucleated and its specific frequency or its location.
Or the location of the cluster.
Right. Yeah, so there have been multiple studies on this that have said different things. We do not see within like the Virgo cluster, we don't see a very strong correlation between nucleation and specific frequency. But what is, so recent work by Ruben Sanchez-Janssen has shown that the nucleation fraction in different clusters is different. So for instance, in the Coma cluster, which is a much more massive, denser environment, a much higher fraction of low-mass galaxies are nucleated than compared to the Virgo cluster. And there are more nucleated galaxies in the Virgo clusters compared to, say, in the Fornax cluster or the local group. So there does seem to be some sort of environmental dependence for nucleation.
Can I have a second? So I just can't restrain from asking, did you check, I mean, have you had an opportunity to check whether the tilting colors that you were seeing with density happens also in the Globular classic UDGs?
What, so this here?
Yes.
We don't have all those colors yet for the UDGs, but that is a good question.
Okay, let me ask a follow-up on what Benedict asked about. So if we assume that the UCDs only form on radial orbits because that's how you strip the material, does the numbers of galaxies you observe or UCDs you observe in clusters correlate well with the number of radial orbits that satellites are on in simulations like in Illustrious?
Yeah, so some people have, I think Joel Peffer also has looked at cosmological simulations to see, I mean, not something where there's hydro, but just to try to identify how many halos could plausibly be the origin, have a UCD in it, and looking at stripping. And what they find generally is that the number of things that we identify as UCDs are, we have many more objects than they can account for in a cosmological simulation. And so, the easiest interpretation of that is, well, we're selecting things observationally. We're not selecting, we don't know what where they were before. And that some of these objects may in fact be just massive star clusters. You still have to figure out why these massive star clusters are on different orbits. But I think the simulations show, so we have about 100 objects we call UCDs in M87. And I think in the simulations that at least that they were doing at Baumgart and Pepper were doing, I think they're getting maybe a third to half that number of objects. So, a third to a half is something where you think that could go away or it could be a problem.
Okay, if there are no more questions, let's thank Eric again. Interesting.
Yeah, I just wanted to follow up on that question, but it's going to get so technical, I thought I'd cut it out. That was awesome talk. Thank you.
Hey, yeah.
I'm Benedict.
Yes, you an email. Thanks for.
So the simulations, how do they simulate that? Because in something like Galaxies, there's no way in hell that you'd ever get anything like this right, resolution-wise and also in terms of just how the stars are created. I mean, there's some stochastic model or something.
Yeah.
Never getting into that strokes.
So I think in this it was very. I think it was dark matter only, and I think they just looked for halos of a certain mass that ended up being stripped.